All right, welcome to our last video lesson in 4.1, orthogonality of vectors and subspaces. In the previous part, we finished with the fundamental theorem of linear algebra, which talked about how the null space was an orthogonal complement to the row space, and then the column space is the orthogonal complement to the left null space. Specifically, the null space and row space being in Rn versus the column space and left null space of being in Rm. And when we look at this piece, we're looking at combining bases, plural, of subspaces. And there's a lot in this portion of the book, and we skipped a little bit. You can see kind of a figure of how the essentially the vectors work together to solve solutions, and we're going to kind of do this a little bit in my example, but I'm not going to write out a lot of the concepts that he writes about in the textbook, just kind of looking at the textbook here. In terms of, I think it's kind of easy to follow, and so I'm not going to hit too much there. I will just kind of highlight a couple pieces of it. So I think the argument is that if we are in Rn, and we're thinking about the conditions for my set of vectors to form a basis for the space or not, remember that the two conditions is that my list of vectors has to be independent and span the space. And so if we're talking about all of Rn, then the perfect number of vectors that would span the entirety of the space is n vectors. And so if we're looking at the set of n vectors that are independent, then that would imply that they span the space because I have enough vectors to cover the entirety of the space, no more, no less. Versus, again, if I have n vectors that span the space, then they would have to be linearly independent. Because I have just the right amount of vectors that can create anything in Rn. And so the takeaway, kind of the argument, is that one implies the other when we are talking about this kind of space and we have exactly the correct amount of vectors. And where this kind of leads into is if I'm looking at a system and saying, okay, well, AX is equal to B, if A is an n by n square matrix, then if there are n pivots, so if I've got n linearly independent columns, then that spans all of our n. This equation is solvable. Independent columns implies that there's a pivot in every single column, which would therefore be in every single row. It's n by n in terms of the size of this matrix. If that's the case, like, this is solvable. Like, there is a combination of these linearly independent vectors which create the columns of A that would result in the vector B in that space. And if these columns are all independent, then they must span the space as well if they're independent. And if that's the case, then there's only one solution to this equation. And so this is where he kind of gets into this idea of, well, if A is therefore a basis for this space, because these vectors are independent, this is solvable, so a solution exists. And if it spans, there's only one unique combination that gets us there. And that kind of conveys two really big ideas of mathematics in the sense of existence and uniqueness. So by looking at the definition of a basis, by knowing that we have the right amount of vectors for a system, independence describes existence, spanning describes uniqueness. And because one implies the other, one implies the other. And if that's the case, if the solution exists and that solution is unique, then we know that A has to be invertible. So I kind of view this section as like a dominoes falling. Once one falls, it makes the other one fall. And we just have this cascading effect of information. And he ends up getting into this idea of saying, okay, well, we could essentially work backwards, that if we're going to say that this system is solvable, then that means elimination produced no rows of zeros, and that means there has to therefore be n pivots, no free variables, So the null space of A can only contain the 0 vector and nothing else. And that means the row space would have to be equal to n. The rank would have to be n. Because we know they're orthogonal complements. And so because they're in columns, if this dimension is 0, the row space would have to have a dimension of n. And that means this is the right number of columns. There has to be n vectors that are independent, therefore they span all of Rn. And I think the main then takeaway from this, and I think this is where the title of this section really kind of comes in, is that when this is not independent and it doesn't span the space, there is no unique solution, but there can still exist a solution. And we've seen this in terms of Unit 3, and that we can express a solution to AX is equal to B as a particular solution plus the null space, the special solution, that there's some kind of combination of those two things. And I think what's really interesting is this example, and in my notes I kind of call this example 2, just because I was skipping around a little bit, is that this now implies that if I have a vector and I have a matrix A, that there can be a unique combination. We can factor that vector out into something that's found in the row space and something that's found in the null space. Because both of those combinations will always result in that B. We can break it down. So for example, just to kind of showcase this work, because it's not exactly written out in terms of the book, is it takes the matrix 1, 2, 3, 6, and the vector 4, 3. And he jumps immediately into how this would break down into something in the row space and the null space, but I want to showcase that. And so I want to look at this, and clearly you can see that the second column is dependent on the first. It's a multiple of 2. And if we take my matrix A and I put it into reduced row echelon form, we would see that combination come out. So for example, if we perform that elimination, just to walk through the process, I would multiply by -3 and then add. So the first row would stay the same. 3 minus 3 is 0. 6 minus 6 is 0. Here's my reduced row echelon form. And now, if I'm looking specifically at the null space of A, the null space of A would be C, I'm just going to call it C2, so some kind of constant, some kind of scalar, times -2, 1. And there's the opposite of that, x2 being my free variable. If I go through and I take my matrix and I find the row space, so in this case if I do A transpose, I take A transpose as 1, 2, 3, 6. We do the same process. I'm going to put this into reduced row echelon form. I would multiply the top by 2 and subtract these two things, so the top row would stay the same. 2 minus 2 is 0. 6 minus 6 is 0. Notice that the row space, a solution in the row space, will look something like, I'm going to put this here, so the column space of AT. This would look like something, and I'll even label it row space, sorry, as C1 times 1 comma 2. Because again, this is identifying my independent column in A transpose. In other words, the first row is the first independent row. So the column space would contain all multiples of that. That's my basis. The null space would contain all combinations of that. That's my basis for the null space. Notice that dimension of 1, adding that together gives 2. So total dimension in the space. That means that if I take these vectors together, they could find every vector in R2. In other words, this vector 4, 3 can be written as a unique combination of these two vectors if I take these two vectors together. And so essentially what we have then is almost like a new system of equations that we're trying to find. Instead of my matrix being A, 1, 2, 3, 6, let's take the vectors that are in each of the spaces, the basis for these two subspaces, and make them 1, 2, -2, 1, so following row space and then column space. if I multiply this with C1, C2, notice how that would actually form the linear combination here. I want to know, how does this combination work to create for 3, my x? So I'm going to vector the x into a combination of my row space and a combination of the bases for my null space. And so I want to solve this system. And you can rewrite this as a system of equations. I mean, we can also go straight to creating an augmented matrix. Or again, I want to perform elimination. So I want to multiply the top row by 2, or -2, and subtract, or add, depending on the way that you want to look at it. And so I'm going to go through and say, okay, times 2 and subtract. So 2 minus 2. I always get ahead of myself. The first row is going to stay the same. 2 minus 2 is 0. Excuse me. 1 plus 4 is 5. 3 minus 8 is -5. Well, I want this to be a 1, so I'm going to divide this by 5. So 1 and -1. Because again, I want to be able to do back substitution, or if I put this into reduced echelon form, it'll identify the correct combination. And so if I multiply this row by 2 and add, it's going to maintain this as a 1, but it's going to zero this entry out. So again, I'm going to multiply this by 2 and add. So that zeros. Multiply by 2 and add gives me this. In other words, notice how when I take the two vectors here, they're linearly independent because they're orthogonal. They're not in the same plane. They're not in the same subspace. So because of that, when I put them together, they're linearly independent and they span. So that means we can create anything in R2 using a combination of the bases. We found that combination here. C1 is 2, C2 is -1. So I can take this vector x and I can represent it as a linear combination of my bases. In other words, x can be represented as a combination of xr, so something taken from the row space, with something taken from the null space. Put null here, row here. And again, by solving this system, we found the combination we need. I can create this by doing twice my row space, so 1, 2, minus 1 from my null space, which you remember was -2, +1. And if I do this combination, 2 plus 2, 4, 4 minus 1, 3. Every vector in R2 can be broken down this way. Notice it's starting with my matrix for A. So we started with a 2 by 2 matrix in A. We were able to find the two subspaces. And now we can take any R2 vector and break it down into something, a combination from the bases of the row space and a combination of the bases from the null space. And this is just dealing with what we've been talking about in terms of the correct number of vectors and it being independent and spanning. Example 4 gets into supposing S is a 6-dimensional subspace, and I left that out of my notes for now, since it's kind of, you can read through it and kind of look through that. But I think the important line that leads us into the next section of this whole unit is that because these two things are orthogonal, there is another way to account for this splitting, which is through a projection matrix. And so that's our ultimate goal in the next lesson, is how can we actually figure out how to split this vector up without solving this? In other words, what's the projection of these vectors onto this one here? What are the, I guess the other way around, how does this vector project onto the row space and onto the null space? Because that'll give me the correct components and how much goes from that. So we'll start diving into that in the next video.